A third issue that we consider in the context of instrumental variables method of estimation is testing for over-identifying restrictions. Testing for over-identifying restrictions. Testing for over-identifying restrictions. Now, while introducing the instrumental variable method of estimation in the model y1 is equal to beta 0 plus x beta 1x plus u, where z is suggested as an instrument for x, covariance xz is not equal to 0, instrument relevance, covariance zu is equal to 0, instrument exogenity. So z must satisfy these two requirements. That is, it must be uncorrelated with the error term, and it must be correlated with the endogenous explanatory variable. And we have seen that even when there are additional explanatory variables in the multiple linear regression model, the second requirement can be, what is the second requirement? Sorry, the first requirement, covariance xz not equal to 0, relevance can be tested. Here we test the relevance like this, that is, x is equal to pi 0 plus pi 1 z plus u with the h0, pi 1 equal to 0 versus pi 1 not equal to 0. So, in the simple linear regression model, this can be easily tested. Now, suppose that you have a multiple regression model, y1 is equal to beta 0 plus beta 1, y2 plus beta 3, sorry, beta 2, z1 plus u1, z1 plus u1, a multiple linear regression model. Again, you can test y2 as equal to, and we assume that the instrument is z2. So, pi 0 plus pi 1 z1 plus pi 2 z2 plus v2. And the exogenity requirement is that h0 pi 2 equal to 0 versus not equal to 0. These are the identification conditions we have discussed. In the case of multiple instruments, say z2 and z3, we test pi 2 equal to pi 3 equal to 0 using an f-test. So, the second, this requirement, the relevance can be tested whether we are considering a simple linear regression model or whether we are considering a multiple linear regression model with the one instrument or multiple instruments. We have also seen that in the context of simple instrumental variable method of estimation, exogenity requirements cannot be tested. Exogenity requirements cannot be tested. That is, here we cannot test whether z and u are correlated or not. But if we have more instruments than we need, then we can test whether some of them are uncorrelated with the error or not. In the simple linear regression model with the 1Z, exogenity requirement cannot be tested. In the multiple linear regression model also with only one instrument, this exogenity requirement cannot be tested. But if there are more than one instrument, we can test whether some of the instruments are uncorrelated with the structural error U or U1. To explain this, consider the model y1 is equal to beta 0 plus beta 1 y2 plus beta 2 z1 plus beta 3 z2 plus u1, z1 plus z2 plus u1 with the two instruments z3 and z4. Actually, only one instrument is enough, but we have two instruments. If there is one endogenous explanatory variable, only one instrument is enough. It is known as just identification. If more than one instrument is available, it is known as over-identification. If no instrument is available, it is known as under-identification, because you cannot estimate this equation at all. So under, just over. So if the equation is over-identified, means if we have more instruments than required, we can test the possibility that some of the instruments are correlated or uncorrelated with the U. That is, what we are testing here is whether the instruments are exogenous or not. Whether the instruments are truly exogenous or not. Now, since we have two instruments for y2, we can estimate one, that is this equation. We can estimate this equation using Z3 only. Using the instrument Z3 only. And suppose that the estimator so obtained is beta star 1. We can also estimate this using Z4 only and call this beta tilde star 1. Beta tilde 1. Beta star 1, beta tilde 1. That is, the procedure is same, two-stage procedure. Y2 is regressed on Z1, Z2 and Z3, then Z1, Z2 and Z4. Then we have in the second stage, we regress Y1 on Y hat and Z1 and Z2. We will obtain beta star 1 and beta tilde 1. Beta tilde 1. So we have two instrumental variable estimators. Now, if all the Z's are exogenous, and if Z3 and Z4 are partially correlated with Y2, if all the instruments are exogenous and Z3 and Z4 are partially correlated with Y2, this point we have explained earlier, then both are consistent. Both estimators are consistent. Now, so if our logic of choosing instruments is sound, the difference between beta star 1 and beta tilde 1 is due to sampling error only. Now, Hosman in 1978, in 1978 proposed basing a test or developing a test of whether Z4 and Z3 are truly exogenous on the difference between beta star 1 and beta tilde 1. A test based on the difference between these. And before explaining this, consider these 3 points. Point 1. If we conclude that beta star 1 and beta tilde 1 are statistically different from one another, we have no choice but to conclude that either Z3 or Z4 or both fail exogeneity requirement. If they are statistically different from one another, then it follows that either Z3 or Z4 or both are not exogenous. Unfortunately, we cannot say which one is the correct. If these two are statistically different from each other, then Z3 may be endogenous, Z4 may be endogenous, or both. That's the simple logic. Unless we assume that Z3 is exogenous to begin with. That we cannot say. The second point is they may be similar. That is, Z3 and Z4 may be similar, even when both fail exogeneity requirements. Such a possibility is there. They may be similar. Of course, both are endogenous. A second problem. The third one is that they may seem different, but statistically not different from each other. We cannot reject the null hypothesis. That is the third issue when comparing two instrumental variables. Anyway, keeping these points in mind, let us consider the procedure for comparing different instrumental variable estimators. Now, the procedure of comparing different instrumental variable estimators of the same parameter is an example of testing over-identifying restrictions. Testing over-identifying restrictions. And the point is, you can test over-identifying restrictions. That is, you can test whether some of the instruments are exogenous or not, if and only if there are extra instruments. If an equation is just identified, that means if there is only one endogenous variable and one instrument, you cannot test it. So you can test this only when you have extra instrumental variables. The general rule is we have more instruments than required to estimate the parameter consistently. Now let us see what is the procedure. So the point is, suppose that we have Q more instruments than we need. Suppose that we have Q more instruments than we need. And suppose that for the endogenous variable y2, we propose 3 instruments, Z2, Z3 and Z4. Then the number of, we have Q as equal to 3 minus 2 is equal to, so 3 minus 1 is equal to 2. Only one instrument is required, but we have 3, so we have 2 extra instruments. It is also known as surplus moment conditions if we use the language of the method of moments. If we use the language of the method of moments, we have 2 surplus moment conditions, Z3 and Z4. And if you use the moment conditions, you will get two additional equations. That is why we are using a linear combination, as we have discussed in the earlier class. Now, let us see. If we have two additional instruments than required, as in this example, if we propose 2 only, it becomes 2 minus 1 is equal to 2. If only 1, it is 1 minus 1, 0. There are no surplus moment conditions, no over-identifying restrictions. We cannot test for endogeneity between, we cannot test the endogeneity of the instrumental variables. So now let us see how we estimate, how we develop the test statistics. The test statistics is based on 2 SLS residuals, 2 stage least squares residuals. Now, in the first stage, what we do is, in the first stage, we estimate the structural equation by 2 SLS. 2 SLS. The structural equation is estimated by 2 SLS and obtain the residuals U hat. Residual U hat. In the second stage, we regress U hat on all the exogenous variables, and we obtain what is known as R square. We denote it as R square 1. U hat on all the exogenous variables. And under the null hypothesis that all the instrumental variables are uncorrelated with U1, n into R1 square follows chi-square with q. N into R1 square follows chi-square with q degrees of freedom, where q is the number of instrumental variables from outside the model minus total number of endogenous explanatory variables. Total number of endogenous explanatory variables. So, for example, if there are 3 instrumental variables outside the model and 1 endogenous, 3 minus 1, 2. If 2 outside, 2 minus 1, 2, 1 outside, 0. This is the reason why we cannot test this possibility for exactly identified equations. And if n into R1 square exceeds chi-square for degrees of freedom q, reject H0. Reject H0 means, when we reject H0, as U hat is regressed on exogenous variables, the value of U hat depends on exogenous variables, means the exogenous variables are, some of the exogenous variables are not really exogenous, they are endogenous correlated with U. If this is less than chi-square q, then we accept the hypothesis that all the all the instruments are exogenous. All the instruments are, if we identify that some of the instruments are endogenous, then we have to find out which one is endogenous, which one is exogenous, and if endogenous regress, instrumental variables are there, these endogenous instrumental variables should be taken out, and we keep only the exogenous instrumental variables. So, in the context of instrumental variables, keep these 3 tests in mind. One, whether the explanatory variables are endogenous or not. Second is whether instrumental variables are truly, weak or strong. The third one is whether instrumental variables are actually exogenous or not. Exogeneity, remember, can be tested only if the equation is over-identified. Means we have surplus instruments. We have extra instruments over and above what is required for just identification. And with this, for the time being, we conclude instrumental variable methods.